Okay, we're on the video with first class Mike Hanling, who's done a great job with his Trident project this last year, so I hope you enjoy this presentation.
Thank you, Professor Roche. The title of our project was Proofs of Retrievability with Low Server Storage, and let's jump right in. Throughout this presentation, we want to make sure that we're hitting what the topic of integrity in cloud computing actually is. We're going to describe what was previously already in the area, in the field, detail what we bring to the field with our new scheme, the actual work that we did throughout the year, and then consider what could be done going forward. So to start off, what is cloud? What is cloud-based computing? We've all really been using it, whether you're using Google Cloud, Microsoft Dropbox, Amazon AWS. You're just taking any local storage that you don't want to have on your actual machine, but you're putting it up in the cloud so that you can use it just about anywhere where you can sign into your account. It's extremely convenient. Like I said, you can access the data from all over the world, anywhere you need to. And it also allows for your own host machine to not have to be so used up. All of its resources don't have to be used. Specifically inside of the Department of Defense, they've been using cloud for a great deal of time, from unclassified all the way through TS and SCI data. The CIA has been using a system set up by Amazon with their AWS service. And even just this year with the JEDI cloud contract that they're trying to push out further and further, all the way to a ship, to a Marine out in the field, the power of cloud computing and cloud storage. So let's go through just a basic example of what our project was really based in. We're going to have a client here, which is just going to be a USNA student. It's going to be a midshipman. They just started the academic semester, and they have these homework assignments for a class. They don't want to keep them on their actual machine, so they just finished their first one, and they're going to put them off on the cloud storage. So now, as they go throughout the semester, they can grab any new homework assignment that they need, and they can complete it. Now, come times for the end of the semester, they've never really looked at that first homework assignment, but they need to review for the exam, and they can get it just fine. But what if that didn't happen? What if instead you offloaded your homework assignments onto the cloud, and you're still going to access your regular ones throughout the semester, but as you can see, that one that was completed is no longer here. The client doesn't really know because they're not checking all the time, but maybe it was deleted somehow. So it comes time for the end of the semester. What do they get back? Do they get nothing? Do they get notified that it was deleted? Are they just going to make it seem as if the client accidentally deleted it themselves? We don't really know what could happen here. And where else does this show up? That was a very trivial example, but what about some other examples? In the legal and medical realms, you need these backups, these huge, massive data stores where you're not really checking them. However, by law, they need to be accurate. They need to be exactly what the client thinks that they are. The same thing goes for intelligence stores. We have loads amount of photos from across the planet. What if any of those were changed? What if it could change to make us start acting upon that data? Another example would be distributed storage networks. Those are becoming more and more popular. It's actually where, instead of having all of your data stored on one cloud server somewhere in the middle of nowhere, to a bunch of distributed networks. So you could have some of your data stored in one continent and some in another. The client shouldn't see any difference. They should still be able to access everything, but it's just how it's stored. Filecoin, especially, as you see here, is actually a cryptocurrency that they use for distributed storage networks, where you get paid a little bit of money for using part of your computer's storage space for other people's storage. So this is very up and coming. Another one would be where you have very important data stores where there is a trusted backup. However, it's going to take a very long time to get to. So examples here that are given are a Marine in the field, or say the USS Reagan out in Japan. They do have standing orders. They have intelligence that they need to make sure is absolutely correct. If something did happen to it where they didn't have that data anymore, it would be okay because there is a trusted backup. However, it would take far too long to get to for it to be operationally useful. So what's the overall problem here? What are we talking about? As you take your data and you store it on the cloud for convenience and for extra computing power, you're relinquishing your direct control. The responsibility of that data now is turned over to the cloud provider, whether that's Google, whether it's Microsoft, whether it's anyone else that you're storing it with. You no longer have 100% control over that data. So how would you know if it's been corrupted? How would you know if it's been deleted? You don't, and that's the point. No major cloud provider actually offers you a way to check this. So how do we go about solving this problem? Generically, what you would want is an audit protocol. You would want to be able, as the client, to challenge that cloud server. You would want to be able to send it something and say, I want to know right now, is all of my data still there? The cloud server would then have to do some sort of computation and give you a response that would prove to you that they actually have everything that you want. And the client would be able to verify that in some sort of fashion. So what's already been done? There's two trains of thought in this field. The first one is provable data possession, or PDP. The focus here is on efficiency. We don't want to have a huge slowdown in user experience. If you want your data, you should still be able to get to it very quickly. You should still be able to check if it's all there very quickly. So the pro is that there's low server storage overhead. So you're already putting things onto this cloud storage provider, and you don't want to have to put a ton of extra in order for these audit protocols to work. And that's what PDP does. However, there is a lesser degree of integrity check. Like I said, the whole point here is efficiency. So there are some ways that a server could trick the client into thinking that they do have everything when they actually don't. And that brings us to proofs of retrievability, or POR. The focus here is exactly what may be lacking in a PDP. It's that greater degree of integrity check. They want to make sure that with a very, very, very high degree of certainty, nearing 100%, if you run this audit protocol, you should know that your data is there. So the pro is that there is a low computation cost. These can usually be run very quickly, and they don't cost that much. However, the con here is that there's a lot of metadata, a lot of overhead storage. To be able to run these audits very quickly, you have to have a lot of extra data already on hand, a lot of pre-computation already done. So where do we come in? We wanted to try to draw a line in the middle here. We know that we wanted the POR, higher degree of integrity. However, all of that extra storage in a true cloud environment, we believe to be a disservice to the client. When you're dealing with cloud providers, they charge a lot more, significantly more, for storage than they do for computation. So we wanted to try to make a trade-off where we have a higher computation for the audit with a lower amount of metadata, of overhead storage. So how do we go about doing that? First, we're going to organize the data into a square matrix. That's what our entire protocol is based off of. From there, we are able to use matrix multiplication to determine if all of your data is still there, which we'll detail in the next couple of slides. In addition, we use a Merkle tree, which is a binary hash tree on top of the database as well. We use this in order to ensure that when you just are retrieving data or you're updating your data, that the server is actually giving you an honest answer. So the integrity check, the audit, is extremely important in knowing if right then all of your data is reachable, but we also want to ensure that every time you retrieve any of your data, the server is actually giving you what it should be. So how do we go about doing this? In the first initialization, this is only run one time. We're going to start on the client by creating a random vector R. So this is going to be square root of the amount of data, so one side of that, and it's going to be all random values. You then have your data matrix M. And what we're going to do is we're going to run a vector matrix multiplication to get S, our secret vector, which is in gold. So now we have the random and secret vectors, and we have our data that we can put off into the cloud. The last thing is that Merkle tree, like I said, a binary hash tree, which we'll put over the data and also store with the data. This is what it will be in the very end. In the cloud, we're going to have the data matrix and this very small Merkle hash tree. On the client side, you're going to have your two vectors and the root of the hash tree, and the two vectors are never shared with the server. And that's very important to make sure that the server is not able to trick you in the end. Now for the audit, this is the centerpiece of our work and what is extremely important. So as we already have on the client side, we have these two vectors, and the cloud server has the data. What we're first going to do is create a new vector of random values, which is the challenge vector here. These need to be fresh values every time in order for this to work. It gets sent over to the cloud server, and we're going to run a matrix vector multiplication again, which is going to give us the orange vector V. This gets sent back over to the client, and the rest of the computation is done on the client side. What's important to notice here is that in this matrix vector multiplication, every single piece of the data matrix M is touched, which means that we know that every single piece of that, if this audit passes, is reachable by the server. On the client side, we have to run two very cheap dot products. You'll see and you'll notice that there is some old, the S in this case, and some new, the C in this case, on each side of this equation. And this is important because this will tell us that if what the client expects and what is actually on the server right now are the same thing. This computation will yield a single value, and if it is the same value, then the audit passes and you know that everything is reachable. If they're different values, then it fails, and you know that there is some piece of that data that the server has, either the server has deleted, it has been deleted in some type of malfunction, but you know that your data is no longer there. Retrieval should be mentioned. Of course, you can retrieve your data under this protocol. You can have any amount that you actually need. And again, we use the Merkle tree structure to ensure that each time you retrieve something, the server is not going to trick you and it's an honest answer every time. In addition, dynamic updates. In the real world, we're updating documents even together at the same time, and we're making edits all the time. So we need to make sure that dynamic updates are supported. Our protocol does support this, and it's actually very easy. Because of the way that matrix multiplication works, it is extremely efficient, and only one value really has to be changed on the client side, and then the actual updated value in the server has to be updated as well. So the big ideas from our protocol. First, the data is treated as a matrix, and we're using matrix multiplication for the integrity check. And second is our major trade-off. We are allowing higher audit computation here in order to get our minimized overall storage. And this will become important because we are testing the actual cost of how much an audit is going to cost the client. So our work performed. This is broken down into two general areas, implementation and analysis. For implementation, this is actually coding. We decided to code this from the ground up using the C language, which gives us the ability to dive very deep down into what is actually happening. We can have everything run for efficiency's sake, even if it's much harder to implement, but it's going to be important so that we can get the fastest results and to make sure that all our results are lining up with the theory correctly. So what does this entail? For the implementation, we had to make sure that the logic and the computation for the client was made, that the logic and computation for the cloud server was made, and then also the communication between the two. We have a custom protocol here for the communication to make sure that we're not communicating too much, but just enough to make sure that our audit protocol works. And again, the Merkle tree implementation had to be done as well. And for the analysis side, we wanted to make sure that we know what is going on in each of the protocols given for the audit, for the initialization, for the retrieval, and for the updates. What we did is we actually took all of this and deployed it in a real cloud environment. None of it was being done on a local machine. We were using virtual machines in the cloud, and we used Google Cloud for all of these tests. And here are some of our results. The graph on the right-hand side is a comparison of our matrix audit, which is the green line, and two cryptographic hash sums, which are the dotted lines. SHA-256 and MD5, as listed there, are two cryptographic hash sums used very widely in today's world. They do provide a similar type of check. However, it's to a lesser degree of security. You can check the sum against what was originally intended and what it is right now to see if they are the same. However, because it's such a small sum, the server could in fact just store the hash sum and send you that whenever you have an audit. That's why it's a lesser degree of security. However, it is touching every piece of your data. And so we wanted to compare to make sure that our audit protocol was not too far outside of what's already being used. And you can see that we fell in between, which is a fantastic result. Breaking down some of the timings on in the table, here's the audit row. And if you take a look at the 10 gigabyte, all these values are in seconds. So this is about a minute. And up to the terabyte size of the database, it actually comes in at about an hour and a half for the server computation, but about 3 hours total on the wall clock. We do achieve the linear progression here as we thought. That was defined in the theory, and it was actually proved through our implementation. However, the disparity that we did not like to see and we were confused about was between the computation time of the server and the wall time. The only other thing that is necessary is the client's dot products, as mentioned before, and those should be extremely cheap. So we wanted to figure out why there was this disparity. So we looked at it, and it took a lot of research to find out inside of the Google Cloud platform what was going on. But we actually found out that it was IO bound. And what that means is that there was a lot of time being taken for the data in the data matrix to be retrieved and put onto the virtual machine for computation to happen. So how can we make this more efficient? The answer that jumped out at us was parallelization. Normally this is done multi-core, which means inside of the same computer, you can have the task split up into many little tasks, all done at the same time. However, in the Google Cloud platform, this was not doable. Even if we did run it on a multi-core system with parallelization, it would give absolutely no benefit because of the way that the virtual machines are configured inside that we have no control over. What we ended up doing was a multi-machine parallelization with MPI. MPI is short for message passage interface. And what we did is we used this, and we had a lot of VMs doing the work of the audit at the same time. So now when we jumped on the analysis, we wanted to make sure that we had very detailed timings. How much was the client computation, the server computation, and the communication when we broke it down? And here are our results. The graph again shows the original lines, the 2 dashed lines in the green, and then our speed ups with 4 and 16 VMs as shown. It is important to point out here that the cryptographic hash sums are no longer a perfect comparison. Those are not made to be run in parallelized settings, and it's actually not possible to do for some of them. However, we wanted to show them here to make sure that you still had an idea of what their run times actually were and how much we were achieving with this parallelization. This graph is a log-log graph, and it does show improvement, but it doesn't really show how much we were able to improve with 16 VMs. And so this graph will show you that, and it's on a linear scale. As you can see, running it with 16 VMs is an extreme improvement over what we had before. You can see the speed up breakdown in the table. And you can see that they are almost linear for the large file size, which is most important. It's not perfect, but it does give you a greater degree of speed up in actual time. The 1 terabyte, which used to take 3 hours on the wall, is actually down to 16 minutes. So conclusions. We implemented this from the ground up. The whole entire code database is around 1,800 lines. That's not a metric to always be used for how much work was put into it. However, that's been refined over the course of actually a year and a half, and it's still 1,800 lines of code. So it shows that we did a lot of implementation with this work. We actually deployed it on the Google Cloud, and it confirmed a lot of our suspicions. So all the theory that we had worked on for a while were confirmed with the test that we had. In addition, once we looked at inefficiencies that were in place, we wanted to make sure that we could find ways to get around this to make sure it is a viable audit protocol to hopefully be used one day. And that's where the parallelization comes in with the near linear speed up. Presentations and report from this work that's already been done. Back in November, we went to the ACM CCS conference. We submitted an extended abstract, and it was accepted and published in their proceedings. I was also able to present a poster at their poster session one night and get a lot of great feedback mid-year so that I could continue to improve upon the work. Later in February, I was invited to be a security scholar at the RSA conference in San Francisco. Again, I got to present a new poster there with the parallelization results, and I was also a finalist in the poster pitch-off, which was the first year that they were doing this, but it allowed us to get in front of a panel of judges, present our work, and actually get critiques on how this could be used in industry. We have a full paper that's in progress of conference acceptance now. And we've also had a meeting with the director of the Warfare Integration Directorate inside of the Chief of Naval Operations Office. And the biggest takeaway from that for us was that he said that he wanted us to implement it for them before Amazon does, and they sell it back to the government for millions of dollars. This started off as a purely academic project. However, after that meeting, it became clear to us that this work could actually be used, and it's fantastic that it's already inside of the Department of Defense and it can be used in any way that they see fit. In addition, our code repository has been made public at the GitHub link provided. So where are we going from here? Potential future work. There are 3 areas in which we see that this could continue to be researched. The first one is that we want to do some more cloud testing with clients all over the world. In the current setup, we did use virtual machines, but they were in the same geographic region as the data itself. So we would want to make sure that this could be utilized with, let's say, a client in Europe and data storage in the US or in Asia. We don't believe that communication will play that big of a role. It will take a little bit longer, but the computation is going to take longer. However, we could be wrong, and that should be researched. Another possible future work for this would be adapting this whole work to be used over an entire database. And by that, I mean an entire block device. So you could run this over all of your laptop storage, over all of your hard disk storage at one time. This could be done through a network block device, and it would be extremely useful. And lastly, we would want this work to actually be used widespread. As I started off this presentation with, cloud providers do not provide the client a way to check the integrity of their data. They should, and we should want that this work will actually get out, and we should continue to refine the work so that it's in a state where cloud providers may actually use it, or where consumers can actually implement it themselves. I appreciate your time listening to my presentation. Thank you so much.
That sound of rousing applause is me thanking you also, Mr. Hanling, for a great job this semester and for your presentation.